or just speak loud or unmute yourself and speak so that I can sort of prepare the revision session accordingly. So if you have any specific questions you want me to address, I can address.
Hello, sir.
Yeah,
this is
hi,
Prof.
Kaushik.
Good evening, sir.
Yeah.
So this.
Just one second. Just one second. So can you all address me as Siva rather than sir? That will be helpful for me. Thank you. Go ahead. Yeah.
Sure, Siva.
No.
I think my problem is, like my lack of understanding is in two areas, which I just wanted to clarify. One is just as a background, right? So in this course so far, we have learned linear regression, machine learning, and all that, and we have kind of drilled into our head a particular model of linear models, which has y is equal to xb plus something, right? And we are learning those parameters, and we understand y as labels or observations that we get and x as coefficients. So that's how we've kind of tuned ourselves, or rather drilled ourselves into our head like that. Now, here the definitions seem to be a little, at least from an understanding point of view, for me, it looks a little from a different angle altogether. So the struggle I'm having is, for example, placing P transpose B, for example, the parametric equations that we talk about. How does that fit in with our general model of where you have y is equal to x beta plus epsilon? And where does this come? And so that's one part of the problem. So this whole parametric equation thing looks a little, I mean, I'm struggling to get the mental model of it, number one. And then one specific question is more around the lecture 4, where we are specifically proving, where where we're specifically proving that the Pxy is a column projection. It's an orthogonal projection of onto X transpose, right? So that's what column space of X. So that specific proof is something that I'm not completely understood. But I think overall that P transpose thing kind of I'm struggling with overall.
Okay, very good. Okay, I'll go with it. I'll tell you how. I'll try and get around that. I'll give you some clarification. Okay, anything else? Anybody else? Anything else to cover?
Shiva, I had a question on the model where we said Yij equals mu plus mu I plus epsilon ij.
Right.
In that model, at one point in time, we said that so we are actually trying to estimate the parameters.
Correct.
And we said that the parameters are not estimable.
That's right.
But why are we formulating the problem like this? In a sense, like if we have multiple populations and each of the populations have some sample data, why can't we say that the sample means are best estimates of the of the respective population means, and the means of means is the best estimate of the overall mean? That is sufficient to is it not sufficient to state the estimation problem correctly? Why are we actually translating it into this model, and then we are saying that these model parameters are not estimable? How come mu and mu ij are not estimable in that sense?
Okay, let me try to sort of backtrack a little bit, and then so I've got two questions here. So I will again, like last time, present something, and then we can have a discussion on that topic again. Did it work okay last time? If we do the same way?
Yeah, sure.
Yeah. So let me just try to present something, and you guys can come back and let me know. See this you will learn slowly in this class. Again, the structure may be a little bit unnerving, but I did not say this in the beginning itself that see there are various linear models one does. So let me just write this down. So there are various for lack of a better word, I'll just use various different linear models one can consider. The meanings of these will come soon, maybe towards week 6, week 7. So among them, the one is called a one-way classification, which is what you observed in a non-estimable setting. I'll explain that in a second. So in a one-way classification, the the setup is, okay, let me write down the list and then we'll come on to this. So one-way classification is the simplest model that you can come up with. There's no sort of a very it's a very basic model that one can consider and work with. There is really no it's sort of the simplest one. So what the idea is that you take your observations Yij, collide the norm Yij, is so you will have each group will have a particular mean, and then there'll be an overall mean mu that's in the group in the population, plus epsilon ij, which is the normal errors that you have in mind. And this will allow you to have different sizes. So you have 1 less than equal to j less than equal to n sub I. Okay. And 1 less than equal to I less than equal to k. This is the simplest model that one can have. It's called the one-way classification model. Then the other model that we'll discuss is these are all models. Why are these models relevant? Will come into specific application that you might see examples. So the other one is called the two-way classification. And I won't do the three-way classification today, but I'll just give you an example of two-way classification, and then sort of we can just stop with that. So this two-way classification is that there are two ways to build this. So one way to build it is in which there are no interactions. So I'll explain what the no interaction between the groups mean in some sense. Let's do no interaction first. The no interaction, what happens is that so you will have the following idea. You'll have one observation per cell. So one observation per cell. Then you can also build with multiple but equal number of observations per cell. You can also build it that way. You can also build it in this fashion. You can also build it with multiple but equal number of observations per cell. Okay. And you could also build it with multiple but possible unequal number as well. So let's write that down. So you could build multiple first. But unequal number per cell. So you could also build it this way. Unequal observations, number of observations. This is the no interaction one. With the interaction one, you could have one observation per cell, and then you could have a sort of a correlation coefficient coming in terms of interaction, which I will not do today. I'll leave it. So this model, if you have a two-way classification model, how will you model it? You'll again have this Yijs, but you'll have to model the interactions in a little bit more, allowing all these groups come in, right? So what you'll have to do is you'll have to have three parameters, Y, I, J, K, and that will have one overall mean, then plus an alpha I for the I place, and then beta J for the jth guy. And then if you want to introduce interactions, you put a gamma ij between I and j. And then if you want to, and you have one possible error for all I, j, k. And then the way you do this, if you want to include all any of these things, so you'll have to do the following for every group. So 1 less than equal to k less than equal to, you can have n sub ij. That is one block. And then you have j blocks like this, and then you have the I coming from the I. So these are just possible models for the data set that you're observing, right? And depending on what application you have, you will have to decide on which one to apply on. That's the broad first part of the story. Why this model is something that you will realize once the application comes into picture. Until as of now, let's just assume that these are interesting linear models available from applications. And I will, maybe in the next review session, I'll come up with specific numerical examples to satisfy one-way and two-way classification. I will do that because I didn't do that in the notes yet. That is first part. The second part is on identifiability, right? So I'll just speak a little bit about it. So then after that, we can it'll address. I'll try to address the P transpose beta question and the orthogonal projection question as well. I will do both of them in one. See, suppose I give you a model, like let's say the one-way classification model, and I ask you, can I estimate the parameters in the model? That's when the model becomes interesting, right? To sort of to work with. So let me just give you the example I gave in the notes, and I'll just do it once more, that we sort of have an idea about how to do this. Give me a second to get the model right. So let's do a simpler one, simplest one-way classification. Let's say we have Yij is equal to mu plus mu I plus epsilon ij. This is a particular model I'm giving you, where I'll assume again mu and mu i's are real numbers, right? Okay. For 1 less than equal to I less than equal to k, and epsilon ij's like I'll assume are IID normal zero. Ij's are all IID normal random variables with mean 0 and variance sigma square. Okay, that's what happens. So how do I think about this model? Let's see. The way you think about this model is that, let's do this. Let's try and go through this model again a little slowly. The way you think of the model is that you have k populations, right? So you have population 1, population 2, all the way to population k. You have k populations, and then in each population you have observations y11 all the way to y1 and 1. Right? And here you have y21 y21 all the way to y2 and 2, right? And so on and so forth. And then you have last one, you have yk1 and up to yk and k. That's how the data set looks like. Is what you have, right? And then you also have this other idea that you have this, and total sample size is n1 plus n2 plus all the way to n3. The total sample size. So then the question I asked you was, can I estimate mu? Right? Can I estimate mu from this? Right? Is this possible? So I have two real numbers, mu and mu I are two real numbers. Can I estimate them? Or can I estimate mu plus mu I? Or so let's see. Let me write the questions down. So the questions are, let me ask the question: can we estimate mu? And that's what I asked you in the question. Then the next question I asked you was, can we estimate mu plus mu I? So, because you can ask, why do we want to estimate these things? That will give examples as I go along, but maybe not today, but next time I'll come into it. Can we estimate mu plus mu I? Right. So these are things that I asked you, and is it possible, not possible, right? So then the formal answer is no, because of the following idea, right? See, I can always perturb this model a little bit. So let me take a new model. Why I just call it y tilde ij. So I call it as mu tilde plus mu tilde I. Okay, that's where the thing is, and then I just have the same epsilon I, which is as before. There's no problem. But what I do with this mu tilde is I just tweak it a little bit. I take a mu tilde as mu plus a constant c that I pick. I pick some constant c that I want, and I do this mu I tilde as mu I plus the same constant c. Okay, this is what I do. I tweak the model a little bit, but then observe that by this tweak, I have done nothing to the model. I've always got y tilde j's is the same as yig. The same model. There's no difference. The models are the same, and yj's are modeled the same way. So in that sense, the parameters are not identifiable. See, the two models y tilde, I can present the y tilde ij as mu tilde plus mu tilde I plus epsilon ij. The sum of mu tilde and mu tilde plus I is same as mu plus mu I. So the normal random variable assigning to y tilde ij is the same as the normal random variable assigned to y ij's. So in that sense, we have two models exactly the same, but the parameters are different. So I possibly cannot have a scheme that will estimate this mu separately and mu I separately. I can't have a scheme like that because the way the model is phrased. So that's a fault of the model, that in this model, these parameters are not identifiable. But you can do something else. I explained in the notes that you can do mu1 minus mu2, you can identify and get. So the next question becomes, how do you decide what parameters are identifiable or not identifiable in the model? That's the next question. So this is means. So let me just conclude this discussion. Then I take questions again. So that means that. So the idea, I'll write this line down. So with these new parameters, we have two models that are the same. With these new parameters, we have two models that are exactly the same. But the parameters are different. So this means that means we have a problem in our hands. That is, we have a problem. The problem means the parameters are not identifiable. That's the first thing to understand. Okay. So then this is the first part of the story. That there's a simple example by which you can exactly see. I have two models that are exactly the same, but the parameters are different. So from this guy, I can't really estimate the parameters. It's just not possible because the model structure is the same, and I have two different parameters. Ideas of the total population and within population. That's the first part. Okay. So now the next part is I try to sort of tell you is that how do I go about identifying, how do I understand the problem of identifiability, and what parameters can I estimate? That's the next part of the question. So for this, I just shifted gears a little bit. So let me just go back and let me write this down. So the above is an example of a particular model where the betas are given by these mu's and mu. So here my beta is my beta vector beta in this case is going to be mu and mu1 up to mu k. And that's what the beta vector is called. Right, so did I make a mistake? Sorry, you're right. Sorry, Kaushik, you're right. I'm sorry. This is neutral. I should put minus C. I'm sorry. I'm very sorry. Thank you for the correction. Sorry. So thank you. Yes, sorry, I made a. That's why they remain the same. I'm sorry. Yeah, thank you. Yeah. Sorry about that. That's why the models remain the same. If it's plus C, the model is different. It's 2C, then it's not a problem. So so what's going on? Let me just give you let me phrase it in this y equal to x beta c situation right here. So the idea is that if I take beta to be exactly like this, vector, right? I think I called it always beta hat or beta bar levels. Right? And I called my vector x, the vector x that I have, the matrix x that I have, as let's say it starts off with all ones here, right? All the first all ones, right? Then 1, 1, and then I have a bunch of zeros, right? And I have a bunch of zeros here, and then for the first n1 guys, right? Then I have zeros again, 1 for the next n2 guys, and so on. That's how the matrix is split, right? And epsilon again would be a epsilon vector would be again the vector would be epsilon 1, 1 up epsilon 1, 2 all the way to epsilon 1 and 1. And then the second one would start, and then so on. And the last one would be epsilon k n k. Epsilon k1. That's all. And this is the transpose would be. And a model would be written as y, the vector y that I have is just x beta plus epsilon. This is what I have. So this is how I would write the linear model, the above linear models. Very good. Now, clearly, the hint is the following, that beta is an rk plus 1 vector, right? And the one immediate hint you can get, that means there are k plus 1 parameters. It's k plus 1 parameters. And that will different ink. Go back to, let's say, k plus 1 parameters. And this one, the rank of x, if you just think about it, is just k, because you have only k independent forms. And that's where the problem is happening. That's why you cannot estimate all the parameters in the model. So this is what I address as I go along in this whole chapter. That is, in linear models, the size of beta and the rank of x will play a role, okay, in understanding, or size of beta, or whatever combination of vectors you want to estimate would be a way to do this. For example, let me just do a slight just to sort of not to confuse you, but sort of just to give you a feel for the above in the above situation here. In this model, you can check that if you look at mu1 minus mu2, if you want to estimate that, let's say, right? Let's call that as some alpha 1, 2, right? This is estimable, right? Why is estimable? Because you can take y11 minus y21. That is a estimate of mu1 minus mu2. Right? It's in fact it's an unbiased one because it's naturally identifiable. It may not be optimal, but it is a estimate. Right? You can even check that that the mean of y11 minus y21 is mu1 minus mu2. Very good. So let me just stop here and take questions. At least let me just understand that the problem is clear. Then after that, we can come and sort of work on it a bit more. So, I'll take questions for a few minutes and I'll come back and go back again. Make it a little bit so I'll take questions and I'll come back. I'll pause for a bit.
Yeah. So this X is basically like a design matrix. You have put it in place just to represent that linear combination, but
correct.
And you're saying that there are problems with this for the simple reason that the rank is just k, and therefore all the individual parameters are not identifiable.
Yeah, I have shown a theorem in week 4 also that gives you that. Right? So I'll show that also. I'll show that also.
Right. Okay. Yeah. So I think this wasn't very clear to us, at least.
I'm sorry.
I took that as gospel. So I took this to be truth. So that's fine. No,
the idea is that I think maybe I didn't present it in a linear way, and that's probably the fault of me. I'm sorry about that. But the idea is the following: you have to play with the model and see what you can do or cannot do.
Right.
And I think the confusion, or the sort of the intuitive confusion having, is the following. See, here in statistics, I'm giving you a model. I'm saying I have a sample from Y's. Can you estimate the parameters? That's the question I'm asking you. I'm not trying to learn some way what the parameters could be in any form.
Yeah.
That's the confusion, perhaps.
Yeah, I mean, that's clearly a reorientation that we are also, at least
exactly.
I've been going through, so that much I understand. Okay, now it's starting to make sense.
Okay, this is the question that I thought I'll motivate the example by an example of non-identifiability and identifiability. But I guess it was not intuitive because you came from a different background. So for me, this is the easiest way to motivate it. But yeah, I made a mistake.
So Shiva, one more question. The presentation of the problem here, when we said we have collection of few y's of from nk parameters, so we are only talking
this is the k populations.
K population.
N1 sample from population 1, nk. That's something you think about.
Yeah, sorry.
Go ahead.
And here we are saying that these are all samples pertaining to only one single variable. Unlike in case of a regression, we think in terms of a dependent variable and independent variable. We do not have that notion yet in this model formulation, right?
You still have that, right? Let's just think a little bit. So let me just make it a little bit clear. So population 1 is here, and this is population k. Okay, it's too small now. I'm sorry for that. So in some sense, you're right. So I have phrased the model in a way I could think of my see what is regression in some sense. You have x's and y's. You think of y as a function of x, and then you sort of you try to estimate the coefficients in front of x. That's what you're doing in regression, right?
Yes.
Is that how you think of regression?
Yes. That's right.
So, but see, the thing is that here it's the same way here as well. In some sense, see, the regression model comes from this particular linear model, in which the errors are random, in the following way. So I'll write it in erasable ink, so that I won't leave it here. So if you look at the expectation of y, right, given the x's, then that's a linear equation, right? Because this guy goes away.
Correct.
And that's your regression model you're doing after. That's just y equal. So when you do linear regression, you're essentially taking this particular model and just computing E of y given x as a linear equation.
Yeah, so the x vectors, x's are kind of we are deriving x's in a way to formulate the regression problem. Can you see that?
Correct. Exactly. That's right. Exactly. Yeah. So your betas are the one you want to estimate.
Okay. So in the second page, in the bottom, you said take y1 minus y21 equals to estimate of mu1 minus mu2. We could have done the same thing for y1 plus y21 also, right? y11 plus y21, because that expectation will be mu1 plus mu2, isn't it?
Yeah, but I want mu1 minus mu2. But yeah, you can. I'm not saying this is a estimate. It may not be the optimal one. It's a estimate.
Correct.
It's a estimate. You can do something else also. I won't be surprised.
So when we have a estimate, then we can do we say that it is not identifiable?
When you can estimate the parameter, then you know it is identifiable, right? So this is a way I can, from the data set, I can estimate the parameter mu1 minus mu2, right?
Correct.
That means that the parameter, this combination is identifiable.
Right. Okay.
I've already told you the individually they're not identifiable because of this tweak in the model, right? I can do what I just said that, right? I can do I can add a C to it and subtract a C to it. The models will be different, but then the parameters are different, but the model is the same.
Okay, got it.
Okay. So now,
can I ask it out, please?
Yeah.
Here in the second page, alpha 1,2 is the the parameter which could be estimated, right?
Identifiable.
Right. One more thing, sir. So your lectures are great, but could you suggest a textbook from which this material is?
Yeah, someone asked me that, so I have made a list. I will send it to Prashant by today or tomorrow morning. I'll do that. I made a list from last time. I was traveling last week. I'll do that today.
Yes, sir. Because the lecture notes, the slides are pretty much easy to go through during the video, but when we have to refer it later back again, it would be better from a textbook. So that's the reason, sir.
See, textbook. Okay, let me try to find one. I have picked it from different textbooks. I'll try to find a bunch of them and give it to you. You can look at them. I'll try to do that.
Sure, sir.
I will do that. I'll give you 3 references. You can take it from all 3.
Sir, the exam is going to be written or is it going to be objective?
It'll be written, I think. Ishan, it's a written exam, right?
Yes, Siva. It's going to be subjective.
Yeah.
So objective or subjective?
Yeah.
Subjective. Okay. Thank you, sir.
Okay, so now let me now clarify the other abstraction that you're struggling with. So this part is clear, right, to most people? Like, yeah, someone asked me a question: is the rank k plus one then identifiable? So we should check it now. So I've given you a theorem next week. We'll try and do it right now. I'll try and do it immediately in a second. So can I just move on, or should I have any more questions? Anybody or?
Just one quick question.
Yeah.
So just following on from that question, coefficients for x. Sorry, I mean what I meant was the coefficients for beta, which is being represented here as x. But in this specific example that we're talking about is just a design matrix.
Correct.
But later on, somewhere down the line, we will be having coefficients. Is that how we should see it progress?
So I don't want to give it names. Let's go with the simple. I don't want to confuse myself and yourself with names and make needless mistakes. Right. Let's go with the following formulation. I have this model for y. Okay, y looks like x beta plus epsilon. Okay, and given y, can I estimate beta? That's all. That's why I go.
Right, and x is going to be this. Like
x is given. X is given. X is given. X is given. X is a fixed matrix given to you.
Okay. Okay. Sure.
X is a fixed matrix given to you. Deterministic. Beta is unknown. I want to estimate beta. That's the model.
Got it. So and in order to sorry, go on.
Go ahead. Sorry. I'll wait.
And in order to do mu1 minus mu2, for example, to estimate mu1 minus mu2,
right?
Would you need a different design matrix such that you will get mu1 minus mu2, or am I?
No, the model is this. This is the model, right? Right. Now, if I look at y1 minus y21, right? If I look here, if I look at y1 minus y21, the mu's cancel off, and I'll just give mu1 minus mu2, right?
Right. Okay.
And that's how I get an estimate for this, right? So if you just look at this, what is y1 minus y2? That's going to look like. It's going to look like. Let me go back here. What is it going to look like? It's going to look like y1 is going to mu plus mu1, right? Mine plus epsilon 1, 1, right? That's y1. Right? Minus y21 is mu plus mu2, right? Plus epsilon 1, 2, right? Or epsilon 2, 1, right? That's epsilon 2, 1, right? And if I do the algebra correctly, the mu's cancel off, and I end up with mu1 minus mu2 plus my errors, that is the normal error that I have, epsilon 1 minus epsilon 2, right?
Right.
So that's how I can estimate, I can use this expression to estimate mu1 minus mu2.
Right. So I don't need a special formulation of the thing itself. Oh, just using
right.
this.
So
yeah.
This comes to your question that you asked me. So what is mu1 minus mu2? That is just, I take the vector p, right? I put, let's say, 0 on the first one, second one, -1, second one, and 0 everywhere else. I take this guy, right? I take this vector p, right? And I take my beta is just going to be just mu1, all the way to mu q, right? Now, if you just stare a little bit, p transpose beta, right? This beta is like this, let's say. P transpose beta is just going to be mu1 minus mu2. Do you see that?
Yeah, I do. Yeah.
So that means this particular linear combination of beta is identified by what I've established here.
Right.
So then the problem we'll pose from now on is that what all p's can I take for which p transpose beta is estimable, is identified, that I can estimate with the model. So let me write this down. So this is one question I have. So it means this, in this case, I've shown you that this quantity is identifiable by the above, right? And I've also shown you that this is not identifiable. If I take, let's say, p tilde to be, let's say, 1, 0, 0, 0, 0, 0, 0, and beta to be the same, I have shown you that this quantity is not identifiable. Is not identifiable. Correct? Is this part clear to everybody that I can express any parameter as a linear combination of my entire vector? Is that clear?
Yeah, it is
Yes.
to me.
Yeah. This clear? This is very clear. So that's how the game shifts now. The game shifts by saying for what all p's. So the game shifts now. Okay, I didn't probably phrase it like this because I wanted to think about it. The game shifts now. So what all p's, which can be any vector. I put zeros and ones. I can put any vector in Rk plus 1, right? What all p's are, sorry about that, are p transpose beta identifiable. Okay. This is what I want to pose right now, a question. That's the first. So is the problem statement clear now? That is what I'm going to pose. So you can take so for example, you're interested in beta 2, let's say. You can take a particular P that will give you beta 2. Because you can take the beta 2 be the one in the second column, third row, and 0 else, that will give beta 2. So is that clear?
Yes.
If you want all the betas, you take k plus 1 P's, and each of them will give you each beta separately. Okay. This is clear, right? So now this is why I go ahead, yeah.
Sorry, just a quick question. So this piece that we have,
yeah,
they have no relation to X, is that in the model that we
that's exactly. X exactly, absolutely. That's why I said X is God given to you. X is God given to you, right? That's part of the model structure.
Right.
X is God given to you. So betas are unknown, Y is in population, errors are normal sigma squared, sigma square is known. Can I find my beta? That's the idea.
So these P's are now a stacked set of P's will become X.
No. P has nothing to do with X. P is
right.
just your favorite vector. You can take any vector you want. For example, if you want to estimate mu1 minus mu2, you take P to be of this form.
Right.
You want to estimate mu, your P is of this form.
So, sir, we cannot estimate.
Yeah.
So, sir, we cannot estimate mu1, mu2 separately.
That's what I told you, right? It's not possible because the model will be the same if I change the parameter. Not happen. Right. That's right. Exactly.
Okay, sir. Is that also because the rank of the X matrix is kept?
That's right. So let's go toward that slowly. Why is that? I gave you a hint. Okay, I gave you a sort of a teaser. The rank will matter. Let's go towards that slowly. Okay. So let's go to now. So is the problem statement clear now? So this is what I want to understand.
Before proceeding, so are we using estimable and identifiable interchangeably here?
Yeah. You can for motor as of now we can do that. So now I'll shift to that. So let me shift to that. Right? Let me shift to that. Let me shift to that. Yeah. So now I will define what do I mean by estimable. Okay. Should I do that now? Okay, let me do that. So now I will define properly. So I will say, this is the first thing I will do. I will say P transpose beta is estimable. I'm going to define it. So remember here, I told you mu1 minus mu2 is estimable because I can have a linear combination of the y's that give me that. Okay. Is that right? Because y1 minus y2 and everybody else gets killed, gives me mu1 minus mu2. Right? And with the fact that the mean matches, right? So I will say now P transpose beta is estimable if, so now what would happen? I would have to have some linear combination of the y's if they exist some L, right? Which is in some vector space. Let's say let's go the same model. Let's go here. Let's go with this model. Let's come down here. Let's go. I have y's. I have x beta. X is given. I have beta as the unknown guy, and epsilon is there. The vector epsilon is there. Let's say epsilon is just a independent guys of n people. Let's take simplest one. So epsilon is sigma squared times in. That is there are n variables. Let's say. So, and beta, the vector beta is, let's say, Rm vector. So I have m parameters, right? And y is an n vector as well. So there is a vector n, L in Rn such that I want to think of L transpose Y as, so I'll write this down in red in a second, as an estimate of P transpose beta. Okay. So again, I'll write this whole thing in red. I want to think of this. I want to think of it like that. So you should again go back to the old picture that I had before. I had y1 minus y2 was what vector? It was this y11 minus y21. That was some L transpose of the entire y. Could just put for some suitable L. And that was an estimate of mu1 minus mu2. Right? That was the old picture that I had there. And I said this was okay because the mean of the y's matched with the mean of was going to be mu1. So I'll just say the same thing here. That this estimable if I have an L for which L transpose of my vector y has the same mean as given by P transpose beta. That's when I say the parameter is estimable. And this should be true no matter what beta is. That is, L transpose y is an unbiased estimator of P transpose beta. Is this idea clear?
Yes.
So if I can find a linear combination of y's whose mean is P transpose beta, I call my vector estimate. The estimate P transpose beta as estimate. This is the definition. Is that clear?
Yeah, it's much clearer now. Sure.
Yeah.
Sir,
That's all I'm
trying.
trying.
Y1, Y21, isn't it estimation of Y1 expected value of Y1 minus Y21?
Yeah, it's right. So I this dot I meant by saying estimate of.
Okay. Thanks, sir.
And I also said here before that is the same as saying that that's the mean of this. That's why I called it estimate. Right? As unbiased one. That's mean matches. So I call this estimable. So that's the same thing as saying. So in statistics, if you go to a statistics class, they'll say the same thing. They'll say that P transpose beta is estimable in your language if there is an L in Rn such that L transpose Y is an unbiased estimator of P transpose beta. That's the definition. That's the game now. So all I have to do is find a combination whose mean is P transpose beta, then P transpose beta estimate. Is this part clear now? This is can you move this down so I'll call this definition.
Sir, one small clarification. L is the learnable parameter, no sir?
Say again?
L is the learning parameter, no sir?
So okay. Let me not throw any jargon to it here. Let's just go step by step. Let's just not.
Sure, I'm sorry.
No problem. I don't want to. I might say something that I might not understand language. All I want to do is, if I have a quantity in terms of beta that I want to see if it's estimable, I have to find a linear combination of y's whose mean is P transpose beta. That's all I would do. So for example, here I want to estimate mu1 minus mu2. I could take y1 minus y21. Its mean was this. That's clear. In the previous case, I said if you want to do only means, that's not possible because I could change the parameters and the means of the y's would be the same. There would be no problem.
So to summarize, it's like we need to find a linear combination of y's which matches a linear combination of P transpose beta. What P transpose beta?
You should find a linear combination of y's whose mean is P transpose beta.
Okay, thank you.
Because each y is a normal random variable with some combination of beta as the mean and variance sigma square. That's what each y is, right? Each y is the normal random variable mean 0 and sigma squared plus x beta. Means just the mean is x beta and then the variance is sigma squared along the diagram. So far so good. Can I move? Yeah, go ahead.
Just one quick clarification. There was also this statement that was said that if you could force, I mean, not with respect to this, but in the previous model, we could force sum of mu I equal to 0, then also it becomes estimable.
That's right. That's right. That you could try. Yeah.
So is that because we're just saying you don't have to estimate mu I at all?
No, if you say sum of mu I is 0 means you can't do this trick. I can't do this trick. If I have that constraint, then I can't jiggle the model.
Okay.
Then I can't have this. I can't have the situation.
Okay, because they'll all move in tandem with each other.
That's right. They'll all move in tandem. It'll shift the mean from 0 to something.
Right. Oh, got it. Thank you.
Okay, this is intuition. I'm not giving you a proof of why this is true. So the proof will come in the next two statements, right? The next two theorems that I've proven in class. Let me just do that right now. So now this is the definition I've given you. I've given you a better one in class notes. Let me do a proper one. Let me give a. So now then the question comes: when is it possible? When can I find this? When can I find this y? Right. So when can I find a y? L. So when can I find an L? So the question comes: when can we find L? Right, that's someone asked me just now, is it a learning parameter or whatever? But I don't want to future that. You give me P transpose B, you give me P, P transpose beta. I want to go find an L. When can I find an L? Correct? This is the question next. So then this is the theorem that I said, the theorem that I said, the answer, let me put the answer down. So I stated this is a theorem in class, but I'll write the answer down so that we all understand it without the jing bang of the notation exploding on us. So I have the same linear model. I have y x beta. So I have, let's say, y. So the model again is the same. Y is a vector. Is an n, and I have x is an n cross m vector, n cross m matrix. Beta is an m cross 1 vector, and sigma, and this n epsilons are n random. A simplest model I take, okay, that way it's clear. So now what I said in class was the proof. I don't want to go to the proof right now, but I'll just say I said in class was theorem was that P transpose beta is estimable. That means I can find an L. That is we can find an L. That is there is an L such that expected value of L transpose Y is P transpose beta. That's what this means. Right? This is true if and only if the vector P is in the column space of X transpose. So this is what answer I gave. So if the vector P is in the column X transpose, then I can find an L for that. That's the proof I've given you in the notes. But instead of doing the proof, let everybody's hopping on the rank. I gave you a teaser. Let's try and see how to sort of get to the rank, how to get to the rank idea. Right? So let's say you believe this answer. Let's say check the proof in class. Let's say you believe the answer. Let's say we believe the answer that P transpose beta estimable only if the vector P is in the column vector. So now let me make a little interactive. So let me just ask you this question. So what is the number of linearly independent estimable parametric function? Let's say it's linear independent estimable. So I call this parametric function. Let's say the parametric is a P. How many can I have? Can someone tell me? Like from this answer, how many such P's can I have that are independent?
As many independent.
Very good. As many independent columns as there are in
as X.
Right? X. Right. Exactly. Right. What is that quantity called?
Rank. Yeah.
Right. So this is the number of estimate function is the same as the dimension of the column space of X transpose. Is this clear to everybody? This idea is clear? So the number of P's which are independent that make P transpose beta estimable are the same as the dimension of the column space extra. Is that clear? If anybody is not clear, let me know. I'll try to explain again. Right, independent rows of X is the same as dimension. That's the same as rank of X. Right? So now somebody asked me this question that, oh, hey, when can I estimate everybody? Let's go through. Let's finish that question and come back to the answer. That means now, if this theorem, if you believe my answer, then the conclusion is this is one corollary. One corollary of this conclusion is that the number of this, right? And let's say you were interested in estimating every beta. So you have that means the simple one from this, the next corollary from this is that if you want to estimate each component of beta, right? So beta is what? Beta is an m cross 1 vector, right? Each component of beta, right? That means what do you do? You take P to be E1, will give you, if you take 1 the first row and 0 everybody else, you get beta 1. 1 the second row, you get beta 2. So you'll have m independent P's to get every component of beta 1. So this is estimable. If you want to estimate this, then let's say if you want to estimate this, then from the above, we need to have. So can someone tell me what the rank of X should be?
M,
right? Because for this to estimate each component, you'll have to have m linearly independent P's, right? Because you have to take 1 each row, right? Because you know that if you take 0, 0, 0, 1 in the ith row, in the ith position, and 0 else, and then times beta, that would give me beta sub I. Is this proof idea clear? Right? That's where the above the old model will fail, because the rank will not be full, and there'll be a problem. This part is clear. This estimable and linear parameterization is clear.
Yeah, just another question I had is this. So this P vector,
right?
May not be necessarily zeros and ones.
Yeah, it could be anything. Exactly, it could be anything. It could be you want to estimate 2 mu1 minus 3 mu2. It's okay, no problem. Yeah, absolutely.
No, what my question is, that really depends on what is given as X, right? So in the sense, because you're saying it's in the column space of X transpose.
Correct. Yeah.
If I'm just given some X, then it's likely that I may get some weird linear combinations, which is lying in that.
Absolutely. So
it's not that I can just ask for mu1 plus mu2. It's really what can be estimable based on the X given to me.
Exactly. That's exactly the question. I asked you the question: when can we find an L? We can find an L only when P is equal. Absolutely. Of course, the way to phrase the question is reverse. You say, someone comes and tells you, I want to find this. Then you go to them, oh, can I find an L? Not the reverse way. But to check how to find an L, you like you said, you check if P is in the column for X transpose. And if the rank of X is M, then you could estimate anybody.
Rank equal to number of parameters, sir.
Correct. So if in this particular model, Y is equal to, the model is Y n cross 1, and n cross M, and n cross 1, this rank has to be full row rank, full column rank. So is this set up now? This setup is clear? No, I just want to go and clean up one more thing and I'll stop for the day, which will sort of identify the idea as well for you. There's no problem. So how does it fit in with this least square estimate, right? So I don't want to go into too much orthogonal projection, which I can do later on, perhaps. It's probably not important for the computational aspects of this class. I just want to state one thing about least squares, and I'll come back and do this. Okay. So I'll stop for the day after that. So let's just do this. So now again, I have many estimates possible, right? So I've given you one estimate. So I told you this thing idea. I have this Y, right? I have this X beta, and I have this sigma squared IN. That is this is the model that I keep in mind. There is X is n cross M, beta is m cross 1, and so on. Right? So beta is Rm, Y is Rn, and X is an n cross M. This is what I have. Right? This is what I have. And this is the variance covariance matrix of the normal, which is sigma squared in the diagonal and 0 is IID sigma squared. So now I said that a number beta hat is called a least squared estimate. A least squared estimate. This goes back to your regression idea, least squared estimate. Estimate if of estimate of beta, or vector beta, if the following happens. If among all possible estimates, this minimizes the distance from x, from y. So y minus x beta. If you look at the distance from x in the L2 norm, its smallest one is given by, over all possible betas in Rm, is given by this person that I have here. So I have this is same as y minus x beta hat square. But I don't have to have the square, no square. So the distance from x beta hat to y is the smallest for beta hat among all possible beta. And then by convention, I just say from this, I'll calculate beta hat like this. Right? From this, the convention I'll just say that I'll just tell you that P transpose beta hat will be classified as the least squared estimate, P transpose beta. That's the convention I'll use. Okay? So I only do this. And then this is the first thing. So this you have seen in regression as well. You just minimize the distance to the line, and then of the sum of squares, and you get the answer. This is what you do. And I think this theorem you have seen in regression as well. That is the beta hat is the solution to x transpose x. Beta hat is x transpose y, right? This you have seen also, I think, in the class, and earlier you have seen this, right? That is that beta hat actually solves it, right? So beta hat is a solution to this. Let me pause here before I make my crucial remark. Is this part clear to you? Or is this idea? Can I just get a quick?
Yes, to me this is clear. Except that this normal equation we had arrived through the derivative route, like.
Yeah, that's right. That I purposely gave a linear algebra proof because I want to make my next remark. But yeah,
right.
If someone gave a doubt, since you know the overall mean is just the mean of individual ones. See, again, don't look at it like a sort of, if you look at it intuitively, like the way you look at it, you're making a small error in the understanding. Just look at it the way I have done it. If I shift the means by C and lower the means of minus C, the parameters change, the model remains the same. So then I can't use that model to estimate parameters. That's how you think about it. So is this clear? This understanding is clear, right? This part is clear. No problem, right? So now let's go back to this mumbo jumbo of the rank, and I'll come back and I'll see, right? So this is why I want to make this remark, right? So here's the crucial sort of punchline from linear algebra now in one shot, right? So have X is n cross n, right? Okay. If X is a full column rank, that means rank of X is m, right? This is a fact that you can easily verify. This implies that this matrix, what can you say about this matrix? Can someone tell me, like X transpose, what will it be? If X is full column,
right? Invertible.
Is invertible, right? Very good. It's non-singular. Is non-singular. Right? Right? That means that beta hat equal to X transpose X inverse times X transpose Y is the unique solution, is the unique least square estimate. That's kind of very, very powerful result. Unique least square estimate. Otherwise, you can have many solutions, but if moment you have full rank, you have a unique least square estimate. And your problem is solved. You don't have to do any more than that. So this is how you connect up independent parametric functions with rank of X. And this is clearly saying that I can estimate beta hat by this correlation. So maybe I'll take 5 more minutes and then finish off that question about orthogonal projection as well, and just sort of understand what's going on. There's nothing much I'm doing.
Just a quick question, sir.
Yeah, go ahead. Go ahead.
If X is full column rank,
yeah,
does it mean that I will be able to estimate all parameters beta? Why would I need a function like P transpose B? Or am I confusing that?
So why you would need it? Once you have all parameters beta, you can estimate any P transpose beta you want, right? No problem.
Okay.
See, you have to look at it from the practitioner's point of view. The practitioner might come and say, I want to estimate mu1 minus mu2. I don't want to estimate mu1 mu2 separately. Right? May not want that at all. But if you have all mu's, you can always estimate any linear combination of automatically. No problem.
Right.
Okay, maybe I'll just quickly go over that other remark that someone asked about this orthogonal projection. I think I went through it quickly in my notes. Let's see if is this the right. This is the
one below, which starts with lecture 4.
Oh, lecture 4 you want. That's simpler one. Okay, that's right. So this is something let me just go through the notes again so it's clear. So I just wanted to say that it's given by the least the orthogonal projection. That's just a fact in linear algebra. That is the idea is that look at this picture that you have the column space of X, right? That's where P lies in some sense. And you have a vector Y. If Y is equal to X beta, then Y minus X beta is 0. So, but Y doesn't lie in the column space of X. That's why you can't solve Y equal to X beta. So Y is like somewhere above, right? And then what are you doing in least squares? Let me go to my notes. In least squares, what are you doing? Instead of doing this, you're trying to find the vector beta hat that's closest to Y among all possible elements in the column space of X. So that's what's happening here. Right? Every X beta lies here, and you want to find the vector here that's closest to Y. And that's given, but in linear algebra, you can easily check that's given by the orthogonal projection of this guy. Right? And that's what I've proved here. So I've just said that's true. That's something you have to check from linear algebra, why that's true. But that's something you can easily check. You could write down any vector Y as something along the perpendicular and something in the column space of X, and that this is the dot product will give you this exactly the closest one. Anybody else will be larger. Is that sort of a crude waving hand proof okay, or you want a more precise
one? No, sure. So I think it was more probably we were used to a different form of that projection where you go with u dot v, like a dot product of.
Yeah, that's right. So I wrote notation like this, but that's probably what confused everybody. So sorry.
Oh, but px is also a vector, right?
Pxy is just a vector. It's just this vector. This vector. This vector. Right? This vector. Right? This vector.
Okay.
And this vector here, let me call this vector yellow. This vector is this is like some number here, right? So x beta hat is the top guy.
Right. Okay, that makes sense. I think it's just I was confused the notation of it. Yeah.
Okay, maybe I'll stop sharing. And if you have any questions, you can ask me. And maybe we can stop the recording on the live stream, and people can ask questions freely here. Is that possible? Or it's okay either way. Okay, so if you have any questions, let me know. I'll stop for that day. I hope this was useful and clarified something.
Absolutely. Thanks, Shiva. It was.
Yeah.
So maybe we can do this every 2 weeks. It'll be useful.
Yes,
that will be
sir.
really helpful. Yeah.
So then I think since I have not understood your motivation properly, maybe I've designed the lectures differently. So again, the key things you have to understand is that when is something estimable and how to find the least square estimate and just work with it. That's it. This whole for this.
Yeah, I mean, some of these, like, L transpose, linear combination of the observations itself is something new. At least what we have seen so far is we are treating them as independent things and we are learning the parameters. So that's how at least I'm used to learning. So now
I think I think I didn't mean to interrupt you. I'm sorry. I think the key is that I kind of deliberately phrase it like a theory first statistics class rather than a sort of an applied statistics class, something, just so that you get a flavor for the theory. So in that sense, I apologize for that. I should give a more example, perhaps.
Oh, no worries. No, I mean, it's just it's a different way of thinking for us. So that's interesting in many ways. So
Okay.
Learning a lot.
I'll send the references across to Ishan by tomorrow morning. You guys can put it up.
Thank you so much.
Okay. Bye-bye. We'll close for the day. Thank you. Okay, Ishan, we're done. Yeah.
Yes, sir. Thank you.
Ishan, sir, when will we get a corrected answer sheet?
For week 1, you get it right.
Week 1. So a graded assignment I have got, but not the. I mean, week 4 have had the most subjective ones.
Okay, so week 1, I think we have released it on the portal. You can check again. Week 2 and 3, we will also do it by tomorrow. Okay.
Okay, sir. The exam is till week 4, no, sir?
Yeah, exam will be till week 4. Yeah.
Okay. So just a request. Next time, I would love if I could have my assignments before the exam.
Yeah. You will get it before exam only. Okay.
Sure, sir.
Yeah.
Thank you,
So
sir.
week 2 and 3, you will get maximum by tomorrow, day after tomorrow. Maximum you will get it. Okay. I think Saturday morning is the maximum.
Sir, I don't have access to previous year. Is there a previous year question paper that we could look for reference?
I think you might find it in some students group. We generally
Okay,
don't
sir.
share it. Okay.
Thank you.
Yeah. Thank you.